welcome all of you to the second day of this conference. So today's first talk is by Professor Benson Farb from the University of Chicago. So he actually needs no introduction. There is those of you who have seen or who are wishing to look into mapping class groups probably will look into this book, the first. And he's today here to speak on Hilbert's 13th problem, its geometry and topology. Professor.
Thanks very much. Thank you for the introduction and for the invitation to speak. I wish I could be there. Today I'm going to talk about some work I've been doing. It's an ongoing project, maybe for the last 6 years, working hard on a single problem, which we haven't solved yet. And it's ongoing joint work with Jesse Wolfson from UC Irvine. Jesse is this guy right here. He's a very, very smart young guy. Can you see my pointer here?
Yeah, we can.
Oh, good. Just making sure. And then Mark Kissin at Harvard, who's a number theorist. And the two papers, if you're interested in material in this talk, I think the introductory paper where you can sort of find what's going on is this first paper. And then the second paper is one of our joint papers that'll come up in the talk. And let me explain what the problem is. I think it's Hazuki Hironaka worked hard on this, and he called this one of the fundamental problems of mathematics. And so let me tell you what it is. Well, before I tell you what it is, let me tell you sort of the theme of the talk. It's relating three kind of very fundamental but different parts of mathematics. One are formulas for the roots of a polynomial in one variable, like the quadratic formula. And this is the formula for the roots of a cubic, which we'll talk about later. And the theory of enumerative algebraic geometry and the theory of modular functions. And don't worry if you don't know, you don't have to know these areas. I just want to transmit kind of the connections between these. And the person who really had this holistic view of mathematics was Felix Klein with this kind of connections. And I would say over the next 100 years, somehow things sort of have diverged a lot. But he viewed these things as sort of the same area. And that's what I want to talk about. So, so let me start with part one of the talk, which is how complicated are the roots of a polynomial in terms of the coefficients. And so a fundamental problem of mathematics goes back to the Babylonians in 3000 BC, is to find and understand the roots of a degree n, we're going to take it to be monic without loss of generality, polynomial with complex coefficients. And a convenient way to study such a polynomial, which people came up with in the 17th century, is what's called an algebraic function. And you can think of a polynomial as giving you a kind of what used to be called a multi-valued function. We now call it an algebraic function. It takes as input, it's a function of n variables, and it takes as input the coefficients a1 through n complex numbers, and as output gives you a set of n roots of this polynomial. The set might not always have n elements, right? You could have a repeated root like z to the n equals 0 has just one root of multiplicity n. So the set can have anywhere from 1 to n elements. Okay, please feel free to just interrupt if you have any questions. Okay. So here's an example of an algebraic function. The first example is the dth root function. So it's the function that takes as input a and then solves the gives you as output the solutions of the polynomial z to the d minus a equals 0, which is of course just the dth roots of the polynomial. So, and more generally, just for experts in the audience, and in fact, this is even what Abel studied in 1800, is the case where the coefficients themselves are in the function field of an algebraic variety. We'll have lots of examples here. And the basic problem is when you're given an algebraic function to try to find a formula for the roots, a formula for the algebraic function. In other words, a formula for the roots of the polynomial in terms of simpler algebraic functions, simpler polynomials. And you want to prove there's no simpler formula. So let's just do examples. So we start out with what's called the universal quadratic polynomial, which is just this function. Sorry, you can see my arrow moving?
Yes, yes, yes.
Great, great. So it's a function of two variables, u2 of bc. It's just the set of solutions of the quadratic polynomial z squared plus bz plus c. And the terminology we write that in is minus b plus the square root of b squared minus 4c over 2. Now, you might say, Benson, isn't it plus or minus the square root of bc and b squared minus 4c? And my answer to you is no. There is an algebraic function called square root. I will remind you of it. The algebraic function called square root is the function that takes a polynomial. It's like a multi-valued function. It's set valued, and it gives you all the roots. So that's what we mean when we actually do the quadratic equation. So you're writing one algebraic function in terms of another. And the key thing is you're writing this algebraic function of two parameters, right? It takes two inputs, b and c. And you're writing it as a composition of the plus, minus, addition, subtraction, multiplication, and division together with square root. That's the point. And the thing I would like to emphasize, there's the square root, is that square root is one parameter function. You only are taking the square root of a number. So when you look at this formula, obviously addition is a function of two variables. If you take b plus c, you have to tell me what b is, and you have to tell me what c is. There's no two ways about it. But the point of the quadratic formula, one of the points I'd like to bring out, is that apart from plus, minus, times, and divide, which are operations that take two inputs, two parameters, what this equation does, what the quadratic equation does, it converts a two-variable algebraic function. It's a composition of just the elementary operations here, the rational operations, together with a function of one variable, an algebraic function of one variable. The variable is b squared minus 4c. So are there any questions? This is like a key point. B squared minus 4c is a single number. You just input that number. So you've kind of reduced the number of parameters needed. And for the cubic, here's a general, not quite a general cubic. Here's a family of cubic equations. You can reduce every cubic to something like this by a linear change of variables. So zq plus pz plus q. So this is a function where you put in the coefficients and you get a set of 1, 2, or 3 elements, depending on how many different roots you have. And this is Cardano's famous formula from the 1500s for the solutions. And it just involves cube roots and square roots. And by the way, as a side note, just to freak you out, if you look, square root has sort of two values. And then the cube root of a square root, there's like 3 values for each of those two. And then there's 3. So I think there's a total of like 12 values. So some of the things are actually wrong. Some of the solutions to Cardano's, when you plug in P and Q here, they don't all give solutions. That's just a side comment that I never realized. I learned this formula in high school. And anyway,
sorry,
the point is
if I'm,
yes.
But this choice of the square root function is the same in both of these, and the choice of the cube root is the same in both of these, or are they?
Well, that's the question. You can start saying maybe we should do that. But even if it's the same choice, it's still 6 valued, as you see.
That's right.
Right. So there's still a problem. But you're right. You probably want to make that choice. Right.
If you do it independently, there should be 36 values, right? Then.
Oh, sorry. Yes, you're right. 36.
Yeah. Okay, thanks. But
Exactly.
You should be doing it the same, or you shouldn't? Sorry, I missed that.
You should do it the same.
But
even then, there's like a problem.
There's a 6
It still won't. Yeah, they'll still give false positives.
Thank you. Yeah.
But the key point I want to bring out is that this is a formula. You've written one algebraic function as a composition of other algebraic functions, square root, cube root, and the arithmetic operations. And the point is, these are two parameter, this is a one parameter function. And in general, of course, the degree d less than or equal to 4 polynomial is solvable in radicals, which means the general degree 4 polynomial, you can express it. It's just a one parameter problem. You only, other than arithmetic, you only have to look at algebraic functions of one variable, namely the dth root, square root and cube root and fourth root. Now for d equals 4, here's the degree 4 arbitrary monic degree 4 polynomial. Here's the equation. So I wanted to illustrate with this that the actual formulas themselves, what are you supposed to do with this? This gives no understanding, right? You want to understand when the coefficients b, c, d, and e start to change, how do the roots start to change? What's happening there? And I think there's a lot to learn even today to answer that question. And as we'll see, a huge amount of modern mathematics, including all of complex analysis and all of algebraic topology, were absolutely invented to solve exactly this problem because the inventors said so. So as you have probably most of you have seen, in degree at least 5, Abel proved in 1824 that the general degree d greater than or equal to 5 polynomial is not solvable in radicals. But less known before this, Bring proved a very beautiful theorem. If you take an arbitrary degree 5 polynomial, you can do some substitutions, in radicals, cube root and square root, and every degree 5 polynomial can be reduced to what we call the Bring radical. What is called the Bring radical. It's this specific equation. In other words, if you give me as a black box that I can solve z to the 5th plus az plus 1. In other words, for every a, it can tell me the 5 roots, which of course the computer can do in 2 seconds. Then I can solve all quintics. And the point is, it's a kind of complexity. The Bring radical is a one variable polynomial. And now there's degree 6. Bring and Hamilton prove that the degree 6 polynomial can be reduced to this kind of two variable polynomial, phi of a and b, a composition of arithmetic operations, some square roots, cube roots, and 6 roots, and this. Don't worry, the talk, I'm not going to just go 7, 8, 9 for the rest of the talk. That'll be the entire talk, but don't worry, that's not going to happen. But the point is, it's 2 parameters, whereas the general degree 6 polynomial, it's 6 parameters, right? Z to the 6, and then there's coefficients in front of the next 6 terms, the 5th power, 4th power, all the way down to the constant term. So the algebraic function, which is the general degree 6 polynomial, has 6 parameters, but you can write it as a composition of one variable functions and this specific 2 variable function. So you might say that solving a sextic is really a 2 parameter problem. And Hilbert actually asked, can you find a clever way to do a substitution to get this down to one variable? And this is the notion of resolvent degree, which was only defined in the 1970s by Brouwer in a never cited paper, and by Arnold and Shimura in an almost never cited paper. But this was a fundamental concept for over 100 years. People knew it implicitly. I won't give you a formal definition. You can look at my papers with Jesse Wolfson, my paper with Jesse Wolfson, and with Mark Kisson. But the resolvent degree of n, it's the minimal number of parameters needed to solve a degree n polynomial. There's a Galois theoretic way to do it, and there's a topology way to do it, a kind of algebraic geometry way to do it. I won't go into those details here, but I think hopefully you get the idea here. So that what we've shown so far, just to summarize what we've done in the talk, we first saw that for any polynomial of degree at most n, you can write it as radicals. There's a formula, so plus, minus, times, divide, and radicals, and therefore the resolvent degree is equal to 1. You just need one variable. It can never be less than 1. You need to do an operation on something. So any questions on that? And then for 5, the arbitrary degree 5 polynomial. So a priori, let me just say this. Let me go back to this. Whoops, sorry. Whoop. Sorry for my. This number RD of n, the general degree n polynomial, monic polynomial, has n coefficients. So it's by definition, RD of n is always less than or equal to n. And we just saw these examples. The Bring radical shows that RD of 5 is equal to 1. And this Hamilton theorem was that RD of 6 is less than or equal to 2. So it's a kind of complexity for solving a degree n polynomial. How simple can you make the formula? And a huge amount of mathematics was motivated by this, starting with Chernhouse. And all of this math can be summarized by saying people were getting upper bounds on RD of 6. I should have said the first theorem was the Babylonians. The Babylonians showed that any quadratic equation, which is a 2-parameter problem, x squared plus bx plus c. There's a b and a c. But they showed you only need to look at a square root, b squared minus 4c. So they showed that RD of 2 is equal to 1. That was in 3000 BC. And a lot of modern work by these people, you can see the huge gaps here. Segre and then Brouwer, and then it was forgotten until Jesse Wolfson and I, in the paper that I referenced, sort of reset the whole thing in modern terms, gave, and you'll see what we did, but sort of reviving this. And then Wolfson, student Sutherland, people have given these new upper bounds. And here's a conjecture. We know a less than or equal to for each of these. We already know less than or equal to due to Hilbert. And Hilbert conjectured the following, that these RD of 6 is 2, etc. And these are called the Sextic conjecture, the octa conjecture, the nonic conjecture. And his 13th problem in the list of most important problems for the 20th century, Hilbert conjectured that RD of 7 is 3. There's a historic reason he should have conjectured RD of 6 is 2. He did in another work, but this is sort of the first unknown case. And in fact, there are no known lower bounds. What that means is that any polynomial of any degree, there might be a formula. If you take a polynomial of degree 10 to the 10, the arbitrary polynomial, so it's 10 to the 10 inputs, you tell me the 10 to the 10 coefficients. I might be able to write that as reduce it by radicals, and then it might reduce to just a one variable equation. It's very hard to believe that's true, and we believe that's not true, and Hilbert believed that's not true. And where Hilbert got these conjectures is he proved, he knew less than or equal to here, and he proved a less than or equal to in these cases. Interestingly, yeah, either everything is equal to 1 or some really interesting things happen. Yeah, anyway, I won't, these are beautiful works, but this is what Hilbert's 13th problem, and nobody knows a lower bound. So are there any questions? Okay, then I'll go to the second part of my talk, which is Klein's point of view and on this whole topic, and it really expands the context. Hilbert's problem, we'll see, is much more than polynomials in one variable. And here's a great quote from Klein. Formerly, the solution of an algebraic equation used to mean its solution by radicals. And even at the present time, such ideas are still sometimes found prevailing. And yet, ever since the year 1858, which is Riemann's thesis, a very different point of view should have been adopted. In other words, what he's saying is, we all learn that, yep, polynomials of degree 4 and less are solvable by radicals, and degree 5 and higher are not solvable by radicals, and we walk away. But there's a lot more than being solvable by radicals or not. There's the resolvent degree. It's the number of variables. And so this is a kind of next step after Galois theory. That's why lots of people were working on it, but people stopped for basically 100 years. But these algebraic functions come up all over mathematics, and this is how Klein viewed it. So here's a first algebraic function. You take, and again, algebraic function, there's a definition. These are like multi-valued functions, but they're basically functions that are implicitly defined by polynomial equations like this. So like the input is a1 to an, and the output is the set of roots of the standard equation here like this. Sorry, this should be a1, or I messed up the, yeah. Anyway, but there's other algebraic functions. You can take an abelian variety, and then so abelian variety is some specific algebraic variety that's an abelian group. It's described by equations, so you can tell me the coefficients describing those equations. And then you have these p-torsion points, set of p-torsion points. So there's a bunch of solutions of equations, and I want to know what are those solutions. And it's the same thing. I can try to reduce equations, and in fact, Klein worked hard on this. You could take a smooth cubic surface, like x to the fourth plus y to the fourth plus z to the fourth plus w to the fourth equals 1. Here's a cubic surface. Famous theorem of Cayley and Salmon. Every smooth cubic surface has 27 lines. So here's two totally different looking, the real points of a smooth cubic surface. Each has 27 lines. So suppose I give you the point. Oh, sorry?
One second.
Oh, Apurva, your mic is on.
Oh.
Yeah.
So what was I going to say? So yeah, so if you give me the equation like x to the fourth plus y to the fourth plus z to the fourth plus w to the fourth minus 75xyz equals 0, there's going to be 27 lines. I'm assuming that's smooth. There's going to be 27 lines. So they're determined by some linear equations. What are those equations? What are the coefficients? Okay. And how many parameter problem is that? And there's other beautiful things like given a quartic curve, there are 28 bitangents. And the function that sends a plane quartic curve to its 28 bitangents is an algebraic function. And so the question is, what is the resolvent degree of all of these problems? And the amazing thing to me is that these problems are all related. And here's one of the connections discovered by Jordan and Klein. And given one line on a smooth cubic surface. So remember, a cubic surface is the solution of a cubic polynomial, a homogeneous cubic polynomial in 4 variables. So it's sitting inside complex projective 3 space. And what does that have to do with the degree 5 polynomial? And here's what it has to do. Given one line, there's a formula for all the others just using radicals and the ring radical, meaning you just have to solve a degree 5 polynomial. So I just connected, or Jordan and Klein just connected a problem about lines on this, 2 complex dimensional manifold, variety with just solving a polynomial degree 5. Totally different worlds. And let me show you a proof of this. So this means, though, that the resolvent degree of the problem, not of finding all the lines, but of finding the remaining 26, given one of them, it's a 1 variable problem because you can do it in terms of this 1 variable algebraic function and the ring radical, which is also a 1 parameter function. So this is, I presented this at a conference and at a workshop, and Steve Treadle, who's a great computer guy, did the following video. So I'm going to show you the proof of the theorem. Again, here's the theorem. Given one line, you can find the others by degree 5 polynomial. So here's what you're about to witness. I'm going to hit start. So what's here? This is a smooth cubic surface, the real points of a smooth cubic surface, the gold. This line lies on the smooth cubic surface. And so what I'm going to do is I'm going to take that line and I'm going to take all the planes in 3 space. Of course, this is all real 3 space and not complex, but we're taking all the planes containing the line. That's a 1 parameter family of planes. And when you intersect a plane with a cubic surface, what do you get? You get a cubic curve. But the cubic curve, we know it contains a line. So that's a linear polynomial. So we know the rest of the solutions, it's supposed to add up to degree 3, and you already have a linear term, so there must just be a quadratic term. Okay, so you get the solutions of a quadratic polynomial, and that's a conic. So here you're getting This is the real points of a conic, so it's just a quadratic. Here you can see it's a hyperboloid. And this picture down here is the intersection of the plane and the cubic surface. And as it rotates, you can see the intersection is changing. And what you can see in this one parameter family of planes, you can write down all of this in equations we do in our paper. In fact, I got it from a book in 1920, a book of Hilton. This was known in 1800s. There are exactly 5 planes where that conic, right? You have this like nice hyperboloid. So it's like a smooth conic. There are 5 times when it degenerates, it's called the discriminant locus. In other words, you can write down when is that conic a product of 2 linear factors, because when it is, that means you get 2 lines, and those 2 lines are contained in the cubic surface, right? And so this gives us 5, you can show there's 5 times this happens, and you get all distinct lines. So this gives 10 lines. So this is actually showing, given 1 lines, you get 10 more just by solving a degree 5 polynomial in 1 variable. And the variable is just like the angle of the plane in this picture. So any questions? Let me show you again, and you'll see it's, smooth. It's smooth, smooth. It's going to be singular in a second. Boom. And you can see it becomes 2 lines. And that's how we found other lines. So we just connected by this beautiful geometric thing. Jourdan and Klein connected 2 totally different mathematical problems. And so that's why the resolvent degree, this is how we view, Jesse Wilson and I review the resolvent degree. It's like relating different problems, relating complexity. And let me just give you one more. Klein and Burkhardt showed that the 4-variable algebraic function that takes a smooth cubic surface to 27 lines can be expressed in radicals in a 3-variable function. This other one that I said, abelian surface to 3 torsion points. These are from totally different parts of mathematics. And so this is quite mysterious why this should be true. So it's saying that the resolvent degree of phi 1, which is, it's the obvious one, it's a 4-variable function, you can write it as a 3-variable function. So it reduces it to, it's less than or equal to the resolvent degree of phi 2. That's the real. And in fact, we prove that the problems are equivalent. And I'll just say that, that it uses this exceptional isomorphism between this amazing finite simple group of order 26,000 something, 25,800 and something, with this projective symplectic PSP for F3. And there are many other equivalences, and you don't have to know what these mean. I just want to, but the key point is that what we proved, me and Jesse Wolfson and I, and Mark Kissen and Jesse Wolfson and I, is that Hilbert's famous conjectures are equivalent. These are all equivalent. So you don't have to know what it means, double 6. These are like very classical configurations of lines on cubic surfaces. And it seems like a somewhat obscure problem, given these kind of 2 6-tuples with certain intersection pattern. I'm trying to get a formula for the other 27 lines. That's equivalent to the Sextic conjecture, that a degree 6 polynomial in 1 variable can be reduced to 2 parameters. And that's equivalent to the problem of finding 2 torsion points in the abelian surface. So these totally different problems are all equivalent to each other. So to me, that's sort of what the modern approach is, like kind of putting Hilbert's problems in a big web of conjectures. We think of it like P versus NP. The resolvent degree might always be 1. It's hard to believe that's true, but it doesn't matter. It's still kind of a framework for connecting all these different problems. Okay. I'd now like to just tell you how Poincaré tried to understand algebraic functions. And the key thing is the multi-valued nature of the algebraic function. So in other words, what we would say today, you have n inputs, and the output is a set of an n tuple, an unordered n tuple. And today we'd say that's just a map from C to the n to the symmetric product, the nth symmetric product of C to the n. And let me give a great example here. Here's the square root. And downstairs, I'm literally moving the number, I'm making a complex number, and Mathematica is just plotting the two square roots. And do you see what just happened? What just happened is we tried to pick, as you all should know from complex analysis class, every number has two different square roots, except for 0 has one square root. And 0 has this amazing this special property that, suppose I wanted to take positive square root. I'm sitting at 1 and the square root of 1 is plus or minus 1. And I decide I'm going to take the positive square root. And I can analytically extend that and just make it an actual function. I'm always picking the positive square root. And as you know, you can do that on any region not containing the origin. But once you contain the origin, you have a loop like this, and you locally define positive square root. But when you come back to where you started, you switched roots. And that was the picture I just showed. We'll come back to that picture. And the key thing that Riemann already knew and realized was that a multi-valued nature of an algebraic function, it's all about the topology of what's called the discriminant locus. It's where the function takes less than n values. It's that locus of points and the complement. So for the square root, you always take two values except at 0. So the discriminant locus is 0. And that somehow going around 0 was the thing that really captures what square root is in the behavior. And here's an example for a cubic. This is the famous discriminant computed in the 1500s, is that this polynomial equation, zq plus pz plus q, you can ask, when do you have 3 distinct roots? And you always have 3 distinct roots unless 4p cubed minus 27q squared is 0. So the set of all parameters where that happens is this cuspidal cubic. It starts to get complicated, and it gets much, much more complicated in higher degree. So this locus of points where when the input like p comma q lies on this locus, this polynomial, the number of roots goes down. And so you think of this as an algebraic curve, 1 complex dimension in 2 complex spaces, and you can take little loops around this, just like we did in the other picture, and solutions you picked change. You can't pick a cube root. And Poincaré's solution to this problem, to really understand what multi-valued function means, he invented algebraic topology. And I say invented because he just plopped down this amazing paper. If you haven't read it, you need to read it. Every mathematician should read this, Analysis Situs. And it's algebraic topology. He defines fundamental group homology and cohomology. And he says explicitly, in order to understand algebraic functions. And so attached to an algebraic function, you have the discriminant locus, and then all these other topology invariants. You have the complement, you have the monodromy, you have the homology, and many, many more. So that's, and the fundamental principle due to Riemann, Poincaré, Lefschetz, is that the behavior of an algebraic function is governed by the topology of the discriminant locus, or its complement equivalent. Okay, that's the key. Remember that complicated formula for quartics? Exact formulas are too complicated. If you want to understand the behavior, you have to understand the topology of the discriminant locus. So let me show you this again. This is just path lifting on, you take the sphere minus 2 points, c hat minus 0 and minus infinity. And I just lifted a loop to a 2-sheeted cover. Okay, that's what that is. It's path lifting, and you lift the 2. So that's how Poincaré realized. So it's an exercise now with fundamental group. There's no continuous way to choose a d root. I always give that to my graduate algebraic topology class. Okay, so they're algebraic functions the way we think of them. In fact, Jesse and I in our paper, we go from a much more algebrogeometric and topology way instead of a Galois theory way. Oh, sorry, was there a question? Okay.
No, I guess not.
Okay, so associated to all these problems, here's our friend, the space of monic polynomials, of all monic polynomials of degree n. That's just c to the n. You're marking down the coefficients. What does it mean to find a root of a polynomial? You're really studying this mapping. It's the set of p comma lambda, where lambda is a root of p. This is an n-sheeted cover of c to the n. It's not a covering space, though. It's a branched cover, right? The inverse image of a1 to an, it's the set of solutions of the polynomial. Generically, the inverse image of a point is n points, the n solutions, right? But there's these special places where a polynomial of degree n has fewer than n solutions. Those places are some very complicated variety in the variables a1 to an, and that controls everything. Similarly, you can do the same for the set of smooth cubic surfaces, which is some huge hypersurface complement, doesn't matter. And then a surface, comma, a line. So the inverse image of a point is 27. Here it's a true cover. It's like 27, degree 27. And it's the same thing for p torsion points. If you don't know the definitions of these things, it doesn't matter. The point is that there's a topological way to understand the general polynomial. Just like for the dth root, how do we now think of the dth root? Not as a multi-valued function. We think of it as c hat maps to c hat, z goes to z to the d, right? And the dth root is the branched cover. It's like the set of z comma w, where z equals w to the d. And then it becomes a function by just taking to w. So it's a Riemann surface. That's why Riemann surfaces were invented. So this is a massive generalization of all that. Algebraic functions. They're everywhere. A lot of modern math came out of it. And I think it's mostly been forgotten. And in fact, Dane in 1928, it had already been forgotten then, because he said at the present time, there appear very many topological papers, which it's funny because what would he say now, right? How many are there now? But when it comes to fundamental problems, we've hardly gone beyond Poincaré or, strictly speaking, Riemann. This, in spite of the fact that such progress would be of great significance for, among other things, the theory of algebraic functions of two variables. So I would say, while the topology of algebraic varieties has been a massive success in the last 100 years, the trying to understand these algebraic functions, like this resolvent degree, this is true today as it was in back then. So let me make the last part here, a historical remark on Hilbert's 13th problem. Okay. So the 13th problem, Hilbert in 1900 at the International Congress posed 23 problems that he thought were important for the history of in the 20th century. What would be the 23 most important problems, like the continuum hypothesis, independence of the continuum hypothesis, etc. And the 13th problem was that RD of 7 is 3. And let me just say, he spent more time on the 13th problem than any other problem. He wrote 20 years later, a kind of survey about where the problems are, and more than half the paper was on the 13th problem, and he specifies very precisely what he meant. But in the original thing, here's the exact wording. I changed his variable f to z, but otherwise it's the exact wording. Prove that the equation of 7th degree, here it is with the 3 variables, is not solvable with the help of any continuous function of only 2 variables. Again, he could have asked for degree 6, was sort of the first open case, but there's a funny historical thing you can ask about later after the talk if you're interested. But what the natural formulation, which in fact he very specifically tells us later that he meant, was that it's not solvable using algebraic functions of 2 variables. In other words, RD of 7 is 3. Solving a degree 7 polynomial is fundamentally a 3-parameter problem, which, because he had already proven he gotten it down to this. That's the natural formulation. And in fact, Arnold, who worked on Hilbert's 13th problem for most of his life, said that I would say this is the genuine Hilbert problem. But why did he use the word continuous? He said, with the help of any continuous function of only 2 arguments. And if you read a lot of the old papers, which basically people who've written about this problem, none of them have actually seemed to have read any of the other papers. They seem to be pretty ignorant, except for Arnold and maybe a few others. But Hilbert says you should find topological obstructions. We've just been talking about the topology of the discriminant locus. And in fact, Arnold phrased this in a really lovely way. He said, you shouldn't even be able to reduce a degree 7 polynomial, not just to algebraic function of 2 variables, but even just continuous functions that are topologically conjugate to holomorphic functions of 2 variables. In other words, you're just using the implications of holomorphicness for the topology. That's sort of, a stronger conjecture. But there's a famous theorem of Arnold Kolmogorov, which I'd like to mention. And here's their theorem. So this is a very cool real analysis theorem. If you have a continuous function on the cube, so it's a function of n variables on 0, 1 to the n, there exists these other continuous functions of 1 variable, so that your continuous function of n variables is a composition and sum of continuous functions of 1 variable. In other words, continuous functions of more than 1 variable do not exist. Of course, here you're adding, so that's a 2 variable function. But basically, continuous functions of 1 variable do not exist. Do you see what this equation is? Do people see? Like, it's on the left is this continuous function of n variables, and here these are just functions of a single variable. And this is very soft. It's like a bare category argument. It's very clever. But why am I bringing this up in this talk? It seems to have nothing to do with what I've been talking about. I agree, but I'm bringing it up because Arnold and Kolmogorov say, this is a direct quote, this gives a complete solution to the 13th problem of Hilbert in the negative. And I was very puzzled by this, but I think what they say is, well, they say, look, here's a function of 3 variables, right? But we just proved any function of 3 variables is a composition of continuous functions of 1 variable, right? And Hilbert said the word continuous. So there are no functions of 3 variables, so Hilbert's wrong. Hilbert's problem is his conjectures are not right. Everything's a function of 1 variable. So how should we view this contribution? I mean, they did say it's a complete solution, but it does show there's like no local topological obstruction. But of course, this theorem has nothing to do with polynomials or algebraic functions. There's no topology. It doesn't use the hypothesis, right? It just works for any continuous function of 3 variables. And by the way, these aren't functions. These are multi-valued. Their algebraic function isn't an actual function. And their thing was about an actual function. And of course, it sheds no light on polynomials. And since this was proved in like 1957, I don't think there's a paper that mentions that paper that has the word polynomial in it. So it obviously doesn't do anything, but it really killed the problem because they just said it's solved. And then everybody who did a survey of Hilbert problems just repeated it's solved, Hilbert's 13th is solved, and it just completely killed it. And people just repeated what other people had written. And I think that's really awful. And it completely killed this wonderful problem. And as Vitushkin said, the problem remains open, and by the highest standards, the range of issues is in fact as broad as it was at the beginning of the 20th century. So resolving any branch cover or any polynomial or any kind of algebraic function of 2 or more variables, or of any number of variables that can't be written as a composition of functions of 1 variable, that's a completely open question. I've been working now, I guess it's 7 years and failed basically. So this is a talk about sort of somewhat of a failure. So the last section of the talk is I just want to give you some inkling of what we've been doing for the last 5 years, 7 years, revisiting the problem today. There are other people who know about Hilbert's actual problem, and the main proponent who said that Hilbert's problem is still open is Arnold. And in fact, he said a lot of the rest of his mathematics was motivation to solve the actual Hilbert problem, even though he had gotten credit as a 19-year-old for solving the continuous version. And in fact, for those of you who know, Arnold's, one of his first big theorems was understanding the cohomology of the Bray group. And he was trying to use that to understand Hilbert's problem, because the Bray group is the fundamental group of the space of monic square-free polynomials of degree n. So let me just say what's been done. Hilbert's 13th it's been placed within the kind of web of conjectures, enumerative geometry, modular functions, which I mentioned earlier. Here are some tools we're using to attack the 13th. I told you there's some kind of monodromy of an algebraic function. So for square root, right, the monodromy is just a permutation. As you move in a loop, the solutions of a polynomial move around, right? As you move a polynomial, the coefficients around, the solutions move around. And when you come back to the same polynomial, the set of solutions comes back to itself, but the individual solutions can be permuted, right? That's what Galois theory is about. But you can follow the tracks and you get a representation not just to the symmetric group, which is a finite group, but to this big infinite group. It's much more detailed information. And in fact, I got into this because I'd been studying braid groups. I'm a Thurston student. And so I knew about braid groups. I'd studied the cohomology of braid groups. And Arnold, in one of his papers, said the real invariant is a braid group, is a braid for a polynomial, but I don't know what to do with a braid. But when I look at a braid as like a Thurston student, I see eigenvalues, eigenvectors, Thurston normal form. Anyway, we're also using geometry of locally symmetric varieties. We've used p-adic Hodge theory. Recently, our latest paper is using prismatic cohomology, and we're solving problems that are, we have solved the problem, I thought it was in one of the slides, but apparently not. We solved the problem that Klein posed in 1888. It's not about resolvent degree, it's about a very closely related thing called essential dimension. The rules are slightly different, but we have obstructions and lower bounds. And I just want to end the talk by showing you an example. Here's the Bring radical. It's a algebraic function of one variable. So what I'm going to do is, here's the value of A. And then what, I shouldn't say Sean Howe did this program. Given A, it's plots, here's A, it looks like it's like 2 plus 2I. And it just plots the 5 distinct solutions. Okay, any questions? If you plug in A is 2, so x to the 5th plus 2 plus 2I, sorry, 2 plus 2I x plus 1 has 5 solutions, and here they are. Now, I'm going to start moving this point around, and as the complex number changes, Mathematica will quickly plot the solutions. But there's going to be a time dimension. They're the roots, like I just said. But now I'm going to not just follow the points, but I'm going to move the whole thing up over time. And what these red points are, it turns out that there are 5 values of A, and these are those points, where this equation has fewer than 5 roots. Fewer than 5 roots. And so that's the discriminant locus. It's this finite variety. And let's see what happens. I'm going to start moving around those points, just like for square root, but I'm keeping track of somehow how the things are moving. And you can see that as I do this, and Mathematica is just plotting them, they start to braid each other. There's more information. It's not just Galois, it's not just the permutation. You get a braid. And so you can see, there we go. So you can see you get a braid. And maybe I'll conclude, I guess we started, but let me just very quickly say, this braid monodromy, there is a proof of concept. The early work of Kurt McMullen, it was related to his Fields Medal work. For degree greater than or equal to 4, he used a braid to do something. You can ask, is there like a Newton's algorithm to solve polynomials of degree n? He used this braid to actually obstruct some problem about polynomials. So it's a little bit of a proof of concept. And maybe I'll just end by saying 2 things. Well, the summary of the talk might be braids, algebraic functions have a rich topological structure relating to discriminant loci, configuration spaces, braids, Galois theory, and more. Beautiful to contemplate. And if you are interested in this stuff, I suggest I would read my first paper with Jesse Wilson, which I referred to on the first slide. But there's 2 kind of sequel talks to this. If you just Google, the Institute for Advanced Study had a special seminar where Jesse and I gave some talks. And you should Google it And those are kind of more details about what I've been talking about. So with that, I will stop.
Any questions from the audience? Please can you hear me?
I have one question, sir.
Yes.
So the resolvent degree is finite for any degree polynomial. Like if you vary all the number n, so is it finite, this resolvent degree?
Yeah, so it's always the resolve. Oh, for the case of polynomials, the resolvent degree of the general degree n polynomial is always less than or equal to n, because it's its own formula for the coefficients. You know what I mean?
Yeah.
Like x to the 57th plus, a1 x to the 56 plus a2. So that is a formula. Right, but you can reduce it already. Let me just point out that we all have seen, like, basically completing the square. You can do a linear change of coordinates so that the n minus first coefficient is 0. So you can always get rid of like one coefficient. And then classically, you can do join radicals and get rid of the next coefficient. And the point is, you get stuck at some point getting rid of coefficients, and you want to know, is that it? So maybe I misunderstood your question.
So what is the maximum degree for which you can compute the resolvent degree?
Yes. So what's the maximal degree for which you compute the resolvent degree exactly? Is that's the funny part. It's 5 because it's equal to 1. We have no lower bounds. So the best lower bound, so for degree 5, it's 1. That's Bring in the 1780s. So I guess you could say the last actual computation was in 1780 something. RD of 5 is 1. And then for degree 6, we know it's at most 2. And we have upper bounds for every n. There's all these people's papers like Sylvester, Hilbert, and then more Wilson and his student Sutherland. So we have upper bounds, but we don't have a single computation because RD could be 1. We don't have any lower bound. It's I wouldn't say the word embarrassing. It's a really, really hard question. It's a really fundamental question. And we found out later, people didn't publish on it, but so we spent like 3 days with Hazuki Hironaka, who had worked on this question in the 80s. So we wanted to talk to him, and he graciously spent a few days with us telling us about his approach. And he taught a course on this in Harvard in the 80s, which got McMullen interested. He thought about this. I know Madhav Nori told me he thought about Hilbert's problem. And nobody had any progress to report, really. And so we have progress on related problems, and we sort of put it in this more general framework. Essentially, I think kind of known to Klein probably. So, but yeah, there's no progress. So hopefully somebody, Mark Kissin said this, and Mark Kissin solved many famous conjectures, but he said this problem is really hard because you don't know what kind of math to use. You know what I mean? When you solve a famous conjecture in number theory, it's really hard. You need new ideas, but at least you know like the area of mathematics, and it's not totally clear. We've sort of thrown everything at it: prismatic cohomology, low-dimensional topology, mappingless groups, Galois theory. It's not. Sometimes it feels like we're making progress, but it's not clear if we have. So yeah. So sorry. The answer to your question is a disappointing. No lower bound. So
I have one last question. So as you told that for degree 6, this resolvent degree is 2. So yeah, so you can write in terms of 2 parameter. So is there any connection like from this? Is there any connection from this to any like abelian variety of genus theory? Like there is some for the genus 2 case, there is the equation is the y square plus y square equal to some p of s, where p of s is of
Yes.
degree 5 or degree 6 polynomial. So, like here you constructed for degree 6, you can construct a nice parameter 2 in terms of 2 parameter. So, yeah, can you is there any connection from here to this abelian variety of genus 2 or 3, like in terms of
Yes.
good deduction or something like that?
So you can look at our paper that I quoted in the beginning. That paper was, I think, with Kissen and Wolfson, the one with Kissen and Wolfson, that where we say that this resolvent degree, we know it's less than or equal to 2 by Hilbert, and the resolvent degree of that problem equals a resolvent degree of finding, I think it was 2 torsion points on abelian surfaces. And so we can prove those problems are equivalent in a kind of roundabout, a little bit of a roundabout way. In this, but they're always kind of these geometric constructions. I mean, I can show you that one. That one is not totally shocking. It has to do with the fact that if you have a degree 6 polynomial, you can mark down where its roots are. That's like 6 points in the plane, and then you can think of those 6 points as lying in the Riemann sphere. And then there's a canonical thing to do when you have 6 points in the Riemann sphere. You take a degree 2 sheeted cover and you get a genus 2 surface. And another canonical thing is to take its Jacobian. And so it turns out that that's a kind of relation, a little bit of a hint as to what we do in the paper. It's pretty elementary, this one. Yeah,
What is the paper you mentioned? Can you just
the paper where we do that, I think it's in my original paper with Jesse Wolfson, or this other paper with Mark Kissen that in the beginning yeah, these are the 2 papers. Yeah. I think it's in this second paper. We relate lots of these kind of questions like this. Abelian varieties come up a lot, of course, which is, or not of course, it's pretty yeah.
Thank you.
Sure. And I will say that this question we answered of Klein worked pretty hard on a problem that he was stuck on, and then we answered because we have fancier techniques than he had. It was on abelian surfaces. His problem was about finding p torsion on abelian surfaces, and the point is the fact that these different kinds of problems are equivalent. I just wanted to say to people, you might start out trying to study degree 6 polynomials, and the space of degree 6 polynomials is a pretty complicated variety, but we proved it's equivalent to something over here about abelian varieties. But the problem about abelian varieties, all of a sudden you have all of number theory, the moduli space of abelian variety, you have all this arithmetic. And like in particular, like p-adic-Hodge theory applies to this, and prismatic cohomology. And so all this arithmetic, you can use all these new tools to solve problems about equations. So the idea is that you use beautiful geometry, like I demonstrated in that video, which is kind of transcendental. Sorry, in that video it wasn't transcendental, but in other things, you use kind of transcendental methods to convert a problem with no arithmetic to a problem that you can use arithmetic, and then you solve it there. So it actually is this kind of web of conjectures is actually a useful tool, I think, in solving these kind of problems. And Hilbert himself gave this surprising upper bound for degree 9 polynomials in one variable by using the lines on a cubic surface. So people like Hilbert and Klein were doing stuff like this all the time.
Thank you.
Benson, one quick question.
Mhm.
Yeah. So you mentioned that for degree 6 polynomials, we can get a hyperelliptic curve.
Exactly. Yeah.
So we can do this for any even degree polynomial, right?
Yes.
That polynomial will give rise to some unique hyperelliptic curve, and then okay. Oh, awesome.
Yes, so you can go one direction. You can reduce one problem to another. In this case, a genus 2 curve, every genus 2 is hyperelliptic, so the problems are sort of equivalent.
Yeah.
But like in your case, you can definitely still try to work on polynomials by taking the corresponding hyperelliptic curve, and you could take the Jacobian if you want to linearize the problem. But if you like MG better, you can do that. And so it reduces the problem about polynomials to a problem about hyperelliptic curves.
Yeah.
And in degree 2, it's special, degree 6 polynomial in genus 2, it's special because they're equivalent, but
okay, so then the problem is that for those polynomials where the discriminant is 0, we will not really get a corresponding.
right.
Okay, so
Right.
yeah, so
But the problem still sort of captures, it's hidden in the problem. The discriminant is in this problem because you're looking at the space of 6 tuples of points that are distinct. So that is the complement of the discriminant.
Oh,
So we are using the discriminant here because when I said take 6 tuples, degree 6 polynomials, I quickly passed to, the whole problem's birational. So I quickly passed to the square free ones. That's a discriminant complement. And when I have 6 distinct points, then I get a hyperelliptic surf genus 2, et cetera, et cetera. So that it does come in.
So would you expect that when we go to the discriminant locus, we somehow have to go to the Deligne-Mumford boundary, or does it not extend the map?
Yeah, no, that is true. That's true. And you can try to use that. I mean, that's definitely a good idea. You could try to use that to get leverage on this resolvent degree. I mean, that kind of thing sort of comes up in some of our work. We didn't do it for MG, but for these AG, like principally polarized abelian variety, we definitely like look at the boundary. You can see some of our paper. So that's a great idea, right? So the discriminant locus is coming in as like the boundary, exactly. So it's really neat. It's we always learn this thing in math, especially in algebraic geometry. It's where things are not generic. That's sort of controlling everything in the world of algebraic varieties. The degenerations, for example, right? It's the same, exactly, yeah.
Question from the audience here. Hello, can you hear me?
Yes.
Hi. So there was a slide where you wrote the Hilbert's 13 problem is equivalent to finding the p torsion points on some abelian variety, right? Something along those lines. So
exactly.
In the case of elliptic curves, at least over C, the torsion points are somewhat well understood. So is there a special case of, can you use that information to solve any special cases of these problems?
No, that's the frustrating thing. I mean, when I say finding the 2 torsion points, you're sort of studying the cover. You have the moduli space of like abelian surfaces, principally polarized abelian surfaces. And then abelian surfaces equipped with a 2 torsion point.
Okay.
And you could take its kind of normal cover. So it's sort of what you call level 2 if you've done this thing. It's the cover where you SP4 F2 is acting on it and the quotient is so you're studying that covering. And so you can we have a lot of information on those spaces. And what's great in this problem, like modular forms come in, all these different things come in, but we still can't get this obstruction of resolvent degree. What we can show is that if you just use rational functions, you can't lower the number of variable. So Klein was coming up with formulas, and he wanted to know if you can kind of just with formulas with rational functions, you can often lower the number of variables. And here we prove that you can't. And it's a kind of question about this covering. You could phrase it in terms of Galois theory of function fields, but it's basically saying there's no rational map from this moduli space of abelian surfaces and this covering space to a lower dimensional pair. It's not the pullback from a covering of a lower dimensional variety. So I just gave you an example of what it means to like use rational functions. So I just converted it to a problem about rational maps of covers of varieties, that a given cover is not the pullback of a cover of lower dimension. So you can see it's very appealing. You can try to use birational geometry and yeah, but the problem is a lot of modern birational geometry, it's just not in, these kind of questions are sort of orthogonal to it. So as far as I know, but Hironaka said this too, not that he's kept up with everything, but I sort of trust him when it comes to birational geometry.
One more. Thank you. That's one more.
Hello, sir.
Sure.
Suppose we have a polynomial over R with a single variable. So
Yeah.
without just looking at the coefficient, can we say anything about the distance of the roots?
Yeah, there's this famous conjecture. Well, firstly, there's this like theorem of Gauss about well, sorry, it's comparing the roots to the roots of the derivative, but yeah, sorry, it's escaping me for the moment, but if you look up like
Are you talking about?
like in the unit circle,
Gauss locus.
the Gauss,
Convex hull.
yeah, the convex hull, yeah. That a root of the derivative is in the convex hull of the roots. Yeah, sorry. So other than that kind of direction, yeah, I'm not sure. One thing I'll say about the methods here, these questions are really interesting over other fields, but so far, and in fact, there's a paper that's coming out, Zinovi Reichstein has started looking at this resolving degree over other kind of fields. But for us, we need algebraically, the complex numbers mostly, but it's really interesting over the reals as well. So yeah, so I guess my answer to your question is I'm not sure. Sorry about that.
Are there any more questions from the audience? Any questions from the online audience? Yeah, so I guess it's time to thank Professor Benson Farb.
Thank you.